quite a few real-life ways that we can talk about oxidation and reduction between the chlorophyll in plants suddenly not growing as much and not causing a green color anymore to what's going on in batteries. So we're going to start talking about how do we look at oxidation and reduction. We'll go through the very basics of how do we assign oxidation numbers, and then throughout the unit we'll look at what actual reactions are with oxidation and reduction and how to analyze and look ahead to anticipate what reactions would happen, and then finally look at some more of the real-life applications of batteries. So why are we learning about this? In general, all reactions fall into one of two categories, either those that involve a change in oxidation numbers or those that don't. Pretty straightforward, as long as we know what oxidation numbers are. So, oxidation numbers, the definition is the charge that would be present if an atom in the compound were ionic. So we're going to look at even covalent things as ionic here and assign oxidation numbers to them. That oxidation number might be 0, but we're going to be applying it anyways. And oxidation numbers are in part due to the electronegativity values of the elements in the compound that we're studying. So we need to look back at electronegativity. So if we think back all the way to chapter 3, so first semester, electronegativity is how strongly an atom attracts electrons of other atoms to itself. And if you remember, the fluorine is our very, very biggest electronegativity value element. It really wants to attract atoms to itself. Francium, on the other end of the periodic table, has the lowest electronegativity because it has so many electrons in between shielding the outside electrons. So we are going to have that break there, easy break of electrons. So looking at electronegativity and oxidation numbers, the atom with the higher electronegativity would be more negative. Obviously, if it's pulling the electrons towards it more, it's going to be more negative. The atom with the lower electronegativity then would be more positive because it does not have the electron around it as often. If the atom in a compound has the same electronegativity, then the electrons will be shared equally. And if you remember, that means that we have a pure covalent compound. So things like the diatomic molecule chlorine would be one of these where the electronegativity would be the same. And in that case, the oxidation number would be 0. So anytime we have one of those one of the diatomic molecules, fluorine, chlorine, bromine, iodine, those are all going to be oxidation number of 0. So you have a big handout that you were given at the beginning of class before moving on to the computer lab. And these are the oxidation number rules. You do need to memorize this. Let's look at methane. So looking at that oxidation rule, we know that carbon is the more electronegative of the substances there. We've got carbon and hydrogen. Carbon is more electronegative. It's going to have the electrons around it more often. Each hydrogen has 1 electron that it can give, so that's up to a 1 positive charge. So each of our hydrogens will have a 1 positive charge. Carbon can take 1 electron from each of those hydrogens, so that means it will have a 4 negative charge overall. And anytime we have a compound, not a polyatomic ion, but a compound that is pure, we're going to have a net charge of 0. So let's take a look at that again. Each hydrogen has a 1 plus. There's 4 of them. That's a 4 plus. The carbon, since it's taking 4 electrons, would be a 4 negative. 4 minus 4 is 0. Okay, let's do some practicing here. So let's look at the gallium oxide. When we have a nice pretty much ionic compound like this, we can just reverse crisscross. We can think about those rules that we had before, and we can see that that 2 initially came from the oxygen, and the 3 initially then came from the gallium. So we have Ga3 plus O2 negative. And overall it has a compound of 0. Our next example, the lead in lead oxide. We know that it's a compound, so overall it has to be a 0. And we know that oxygen is always a 2 negative. So 2 times 2, we have a 4 negative based off of that oxygen. And we know that we need a 0 overall. So that means my lead, Pb, must be a 4 positive. So we can take a look. Whenever we have a compound, we need to make sure that the sum is 0. And if we know certain ones, like oxygen, it's not a transition metal, it's one of those nonmetals that we always know, we can figure out what it is. Our next example, if I have potassium bromate and I want to figure out what the bromine is, I can look at the things that I have along with it. So potassium, if we look at the periodic table, is a 1 positive charge. The bromine we know should be a 1 negative based on where it is in the periodic table. But let's make sure we actually know what it is. We know that oxygen is a 2 negative, and there are 4 of them, so that's a -8. So overall from this, we have a -7, and we know overall we need a 0. So in this compound, bromine is actually acting a little bit different than we're used to. It's going to have a +7 charge. Okay, if we're looking just for the manganese in this compound, again, oxygen is always going to be a 2 negative. And we've got 4 of them, so we have a -8. Potassium is always going to be a 1 positive, and there are 2 of them, so we have a +2. The difference there is -6. There's just 1 manganese, and it must have a charge of +6. It's having 6 electrons pulled from it most of the time. Okay, here we have something that has an overall charge. An overall charge this time. So we're not looking at exactly what we had started with before. We're not looking for a total of 0. This time we're looking for a total of -1. And let's see here. We have 2 hydrogens. Hydrogen is going to act as being a 1 positive, and there are 2 of them, so we have a 2 positive. We're looking for a net of 1 negative, so our value that would make that so would be a -3. Again, we're going to look for a total this time of a -1. And if I look at my rules, I see that we have oxygen, and oxygen is always a -2. There are 3 of them, so I have a -6. Overall, I need a -1, and I have something that needs to go there to get that, it would be a positive 5. So my iodine is a positive 5. Okay, another one that's charged, and we've got some polyatomics in this one as well. Got a lot going on in this one. Okay, we're looking for aluminum. Overall, I'm looking for a 1 negative, and I have a bunch of oxygens to start with. I have, but I do have a polyatomic, which makes life a little bit easier on us. I have the OH group, and I have 4 of those OH groups. OH is always going to have a 1 negative charge, so I multiply that by 4, and I get a 4 negative. I need a 1 negative overall, so my number that needs to go there is a 3 positive. Aluminum is a 3 positive charge, which if you look at the periodic table, that one makes a lot of sense for us. One more example with these. If I'm looking for the phosphorus in H2PO4, 1 negative. I'm looking for 1 negative overall. And I can't look at the PO4 as a group this time because I'm looking for just the phosphorus in it. So it doesn't work like the hydroxide in the last one. Hydrogen each have a 1 positive, and there are 2 of them, so we get a 2 positive. And the oxygens are all going to be 2 negative, and we have 4 of them, so we have 8 negative. And we are looking for a 1 negative overall. Here we see that we have a 6 negative. A negative 8 plus 2 is a negative 6. And if I want a negative 1, that means that my missing number has to be a 5. So my phosphorus is a positive 5. Okay, polyatomic ions are a little bit different for us. We determine the oxidation number of all of the elements in each of the following. And so we're going to look at the ions that are present. So if we have Fe2CrO4 3, and I want to figure out what we have overall, I can look at, I want to just find the chromate in particular. Please note that this negative doesn't actually mean anything there, it's just our example. So we're going to be looking for the iron, and we want to look for what that is overall. To be able to do that, we need to figure out what's going on with the chromate overall. So if we have CrO4, we know the oxygen always. Oxygen, is a 2 negative. We're multiplying it by 4 to get 8 negative. So the only thing I don't know here is what my charge of chromium is and what the charge of my ion is. Once I know those two things, I'll be able to figure out what my chromium and chromate charge are. What I can do is look at my value here, right behind the iron. That came from CrO4 to start with. And this 3 then came from that iron. So my iron is a 3 positive, and my CrO4 is a 2 negative. So my ideal number here is a 2 negative, and so my value of the chromium would be a 6 positive. Let's see we're just playing a game back and forth with these values. You can try the rest of them on your own. They should be pretty straightforward, using the same process each time. We already figured out that we can look at the overall charge. This time, mercury, we're not sure which mercury it is. It's most likely either mercury 2 or mercury 4. If you looked at your polyatomics from the beginning of the year, you could assume that it's mercury 2 because Cr2O7 is a 2 negative charge overall. So you could go through and figure out which each of those elements would be. And PO4 is our last one. You know that phosphate is a negative 3 charge from all of our practice with acids and bases. And you also can see it here because